I'm Krisa May Marcolita, and today we're exploring how phase change materials or PCMs are transforming the world of civil engineering, especially when it comes to making buildings like that more energy efficient and sustainable. Let's go! Have you ever wondered how buildings can be designed to naturally regulate their temperature, reducing energy consumption and enhancing sustainability? The answer lies in an innovative technology, phase change materials or PCMs. These materials harness the principle of latent heat storage and cleaver chemistry to absorb, store, and release energy, creating a balance between external and internal temperatures. Let's dive deeper into the fascinating chemistry behind PCMs and how they are transforming the construction and engineering industry. So, what are phase change materials? Phase change materials or PCMs are substances that undergo a phase change typically between solid and liquid at a specific temperature range. During this phase change, PCM absorb or release latent heat without a significant temperature change. This unique property allows PCMs to stabilize indoor temperatures, making them invaluable for energy-efficient building. So, for example, during the day, PCMs can absorb excess heat when the building warms up, and at night, they release that stored heat and they solidify, helping to maintain comfortable indoor environments. Phase change materials can be categorized into three main types, each with distinct chemistry properties and advantages. So first is the organic PCM. Organic PCMs include materials like paraffin waxes and fatty acids, and they are made up of long-chain hydrocarbons, which melt and absorb heat when the temperature rises. So the chemistry behind this involves breaking weak intermolecular forces called van der Waals forces between the hydrocarbon chains. As the material cools and resolidifies, these forces re-establish, releasing the stored heat. Organic PCMs are popular because they are non-corrosive, chemically stable, and available in a wide range of melting points. However, they have lower thermal conductivity compared to other PCMs. So the second type is the inorganic PCMs. Inorganic PCMs, such as salt hydrates, are another common category. These materials are known for their high latent heat capacity and higher thermal conductivity than organic PCMs. Their phase change often involves the absorption or release of water of crystallization. So, for example, sodium sulfate decahydrate melts to form sodium sulfate and water. However, while effective, inorganic PCMs can be corrosive and may experience issues like subcooling and phase segregation. So lastly, we have eutectic PCMs. These are a mixture of two or more materials that melt and fuse at a specific lower temperature compared to the individual components. Eutectics are highly efficient because they can store a large amount of energy while maintaining a precise melting point, making them ideal for use in building materials. The chemistry behind eutectic mixtures involve combining materials that creates a uniform solid-liquid phase transition at a specific temperature range. These materials are perfect for application requiring exact temperature regulation. So now, let's talk about why PCMs matter for buildings. Buildings consume about 40% of the world's energy primarily for heating, cooling, and lighting. By using PCMs, buildings can manage indoor temperatures more effectively without relying so heavily on active heating or cooling systems. PCMs can be incorporated into walls, ceilings, and floors, where they absorb heat during the day, keeping interiors cooler, and then release it at night when temperature drops. So, how are PCMs used in buildings? To incorporate these materials into construction, they are encapsulated to prevent leakage and degradation during the phase change process. So first is the microencapsulation. Microencapsulation involves enclosing tiny PCM particles in a protective polymer shell. This keeps the material stable and prevents leakage. So second is the macro encapsulation. Macro encapsulation uses large containers or capsules that house the PCM, which can then be embedded directly into walls. Furthermore, once encapsulated, PCMs are blended with common building materials such as concrete, gypsum, or insulation boards. When the building heats up, the PCM absorbs excess heat during its melting phase. Later, when the temperature drops, the PCM solidifies, releasing the stored energy. Nowadays, there are already several examples worldwide where PCMs are being used in real buildings. For example, some commercial buildings have PCM-infused wall panels that helps regulate door temperature and reduces air conditioning costs. Another example is in hospitals, where PCM materials help keep temperature stable for sensitive equipment and comfortable for patients. So, while PCMs have immense potential, they also face several challenges in their applications. So, the first challenge is the compatibility. PCMs must chemically bond well with the most building material to ensure durability. Second is thermal stability. So, over time, repeated heating and cooling cycles can degrade the material. Third is corrosion. Inorganic PCMs in particular can be corrosive and may require the use of stabilizers or inhibitors. So lastly is cost. The encapsulation process can be expensive. Despite these challenges, the benefits of PCMs are undeniable. Building integrated with PCMs consume less energy for heating and cooling, reduce carbon emissions, and create more comfortable living and working spaces. As research advances, we can expect PCMs to become more affordable, durable, and effective, paving the way for their broader adoption in green construction. From homes to offices and industrial spaces, the chemistry of phase change materials is playing an important role in designing the sustainable cities of tomorrow. Innovation in material science, particularly with phase change materials, is helping us create buildings that are not only smarter but also kinder to the planet. By understanding and harnessing the chemistry of PCMs, we are taking a significant step toward a more sustainable future. Again, I'm Trisami Mercalita and thank you for joining me on this journey through the fascinating world of PCMs and their role in building materials.